For our new chapter, we're going to start with functions and their graphs. We're actually going to start with just a relation. A relation is just, in this case, a list of ordered pairs, and x that goes with the y and x that goes with the y. And I want to remind you that domain is always the set of all x values in the relation, and range is always the set of all y values. So if we were going to write the domain for the relation shown in the brackets here, we actually say it's the set of all of the x values represented. So we would take each of those x values and just make a list of them. I like to write them in order, but I suppose that's not required. And then for the range, same thing, only this time I'm going to look at the set of all of the y values, so the second ordered pair. Again, if you'd like to write them in order, you can. Notice that I only had to write that one that showed up as an output right here. Those are both part of the range, but I only need to list it once. For the graphs, this could be a little bit trickier, but again, thinking about domain, I like to think of it as sort of like, how wide is this? So this graph kind of goes width-wise from -5 to 5, right? And so for the domain for this one, I'm gonna say it goes from -5 to 5. And that closed circle means I'm including the -5, open circle for the +5. Let's talk about range on the same graph. For range, I'm trying to see how high and how low this graph goes. It looks like the highest it goes is up to 6, the lowest it goes is down to 1. So the range would be from, well, let's put the smaller number first, so 1 to 6. That 6 is included and the 1 is not included. Next graph, the domain. So did you notice that this is like infinitely wide? So I'm thinking on the x-axis, all of these x values are represented because this graph continues on forever. It goes all the way to the ends of the x-axis. So because of that, I'm going to say that the domain is all real numbers. And in interval notation, we would say that stretches all the way from -infinity to infinity. And then for the range, well, it doesn't actually hit all of the y values. Like this branch of the graph hits everything 2 and above, and this branch of the graph hits everything 2 and below. So the range is actually 2 intervals. It's the bottom one, which goes all the way down from -infinity to -2, but then union that with the other branch that starts at 2 and goes all the way up to infinity. The definition of a function is important to remember. Each element in the domain corresponds to exactly one element in the range. Each input has exactly one output. I'm going to write all the inputs from this relation here and all the outputs over here, not in any sort of order, but then we call this a mapping diagram. So the 4 goes to the 7, the 3 goes to the -2, the 6 goes to the 1, the 7 goes to the 1. And what we're checking for is to make sure that each of these x values only has one y value. So does 7 only have one y value? Yep. Does 6 only have one y value? Yep. And so even though they have a repeated y value, it's okay. So this one is a function. Yes, that's a function. This one, 5, 2, -4, and there's another 5, so I'll only write it once. -3, -2, 1, and 1. Let's see. So the 5 goes to the -3, 2 to -2, -4 to 1. Why did I write the 1 twice? I don't know. And then this 5 matches to the 1 as well. And actually that's a problem, isn't it? Not because it mapped to the 1 twice, but because of this 5. This is the violator right here. It says that each x is only allowed to have one y, because that 5 maps to more than one y value. This is not a function. The way that we test it on a graph is we look at, for example, do you see this x value at -5? Here are all the places the -5 could be represented. This one only hits once, so there's only one output for that x value. Same with -2. There's only one output for that x value. The problem comes when we get over here, like in the 2s and 3s. The number 2 or the number 3 is going to have 3 different outputs, and each input is only allowed one output. We call this the vertical line test, and it's a fail if it hits more than once, because each vertical line stands for an input. So this is not a function. This one would be okay, I believe, because each vertical line only hits once. No violators makes that yes a function. Doesn't matter how pretty the graph is. If a vertical line hits twice, that means an input has 2 different outputs. That's a no. This one is looking good. The only sketchy part is right here at x equals 2. How are you feeling about that vertical line? It definitely hits here. But did you know that this open circle means that there's not actually a point there? If there's not a point there, then even that vertical line only hits in one spot, so this is considered a function. Sometimes we're going to just look at equations to decide if these are functions. One way that'll probably make the most sense to you is we're going to try to just get the y by itself on each of these. Divide everything by -1, that goes y equals -18 plus x. So that just means each x that I put in should only give me one y value, and so this is a function. Watch what happens on the next one. If I subtract the x, I divide by the -1, and then I take a square root. Remember, when you square root both sides, you need the plus or minus. And now here's the deal. When I plug in an x value, I'm automatically going to get 2 outputs, right? The positive and the negative output. So that one is not a function because each x value will lead to 2 y values potentially. So if you start to see the pattern, as long as your y seems fairly innocent, if it's just going to solve for y equals something. If I plug in an x now, each number only has one square, and then I negify it and add 3. That's only one output. Really, it's the only time you have problems is with that plus or minus. So this one's fine. That one's a function. How about this guy? Solving for the y, so we're going to add the x. Take a cube root. Do you need a plus or minus with a cube root? The answer is no, only for even roots. So since we didn't do an even root, this would just be a cube root of 9 plus x, meaning that each x value is only going to give us one y value, and that is a function. So it would only be a problem when we have those even powers of y, basically. But I would like to see you solve those for y, so you can show me how you'd get those 2 outputs, the plus or minus, when you do an even root to both sides. Evaluating functions. When you first learn about functions, you sometimes think that this says f times x. We learned fast that means f of x, the function value of the input x. And so this one's asking me what is f of 3. So it's telling me when I input at x equals 3, what is the function value? And it's really just a game of substitution. Anywhere you see an x, we're going to sub a 3. And in this case, we can figure out the actual number. So 21 plus 9, that would be 30. By the way, the value of the function is 30. That indicates that that would be the y value if we want to graph that. So when the x is 3, the y would be 30. We're going to be doing some fancy algebra now, where we have inputs that are, you'll see why this is important later, but what we're going to do is we're going to take this guy, and wherever I used to see x, I'm going to replace those x's with a negative x. Here's how it's going to look. So instead of 7 times 3 or 7 times x, it's going to be 7 times negative x plus negative x squared. So again, just substituting. And then simplifying. This would be a negative 7x. In this case, a negative x times a negative x would just make a positive x squared. And that's all you're expected to do. We're not really solving anything. We're just finding what the function looks like with an input that's the opposite of the x value. This one's real fun. We're going to put an x plus 2 as the input. Again, if we had 3 as the input, we put a 3 here and a 3 here. If we have x plus 2 as an input, we're going to put an x plus 2 here and an x plus 2 here. It should look like a substitution. Anywhere you see an x, you'll put an x plus 2. And then you just have to work on simplifying that. So we're going to distribute that 7. For this, make sure that you don't fall into that trap. You all know that this is supposed to be x plus 2, x plus 2. We're going to have to FOIL that out. So foiling that out would be x squared plus 4x. Sorry, maybe I shouldn't skip that step. When I FOIL, x squared plus 2x plus 2x plus 4. That would be that piece. And then we just combine like terms. So this is the function that represents f of x plus 2. On a graph, I just want to remind you that the number inside is the input. So they're asking me what's the value of the function g of x when x equals 0. So I go to where x equals 0 and I see where the function is at x equals 0. I see that there's a point at 0, negative 4. Therefore, the value of the function at 0 is negative 4. Again, the answer to each of these is a y value. Next one, g of 2. So I'm going to go to where I see 2, and I'm going to see what the value of the function is right there. The y value is up at 4. And this last one reverses it for us. So this is saying the value of the function equals 1. So g of x is just another name for y. So the y value equals 1. The y value equals 1. What is the x value? There's actually 2 spots that have a y value equal to 1. So we would say that x equals 1 and x equals 5. That's not a function violation though, because each input still only has one output. It's okay if they have the same output. There's a couple of problems in your assignment where it's going to have you make graphs using just a little table of values. It's going to tell you what to put in for the x values, and then you just have to plug it into the function to find your y's. On the second graph, which probably they should have called this one g of x, but on the second graph, it tells us to pick a different set of x values and then plug those in. So this time 0 minus 2 squared would be 4. 1 minus 2 squared would be 1. 2 minus 2 squared, 3 minus 2 squared, 4 minus 2 squared. And you might notice that the f of x values, the y values, all match. Let's see what that looks like on the graph. Are you seeing how that second graph is actually just a shifted version of that first parabola? And did you notice that it shifted to the right? So this one is shifted to the right from the first one. The reason I bring this up is because we're going to talk about transformations again this year. And even though it says x minus 2, which might have you thinking left 2, the reason this is a right 2 is because it takes an even bigger x value to compensate for that minus 2. To get the same output, we need an even bigger input. And that's why it's shifting to the right, because that subtraction of 2 is making it so our numbers have to be bigger, actually. So that's why it always seems opposite on those horizontal transformations. It's because it requires a bigger or a smaller x value to do what it used to do with just a regular x. Interpreting functions. I like to think about the label all the time on these. The sale of a new style of shoe on a certain website is modeled by the function n of x, where n is the number of pairs in thousands of shoes sold x weeks from release. So the x is the weeks, always helpful to label, and n is the number of pairs in thousands. Explain what these function values represent. So when it says n of 10 equals 12.5, remember, this is representing an input, and this is representing an output. So the input, the x value, is the weeks. So 10 weeks after release, we would be selling, well, 12.5 thousand. 12,500 pairs. Is how many we would have sold in, I guess, in week 10, right? How about the y-intercept? If we go over here, I'm noticing it crosses at 6. It might help you to write that as an ordered pair, 0, 6, because then you can remind yourself of the labels. Week 0, which is release day, right? They sold 6,000 pairs. And then x-intercepts, looks like it's about 15 and a half. Again, x-intercepts always have a y value of 0. Y-intercepts always have an x value of 0. And this is talking about week 15 and a half. So partway through week 15. These are not going to be very popular anymore. We are going to sell 0 pairs. They've run their course, not very popular anymore. So I just encourage you to use the ordered pairs, use the function values, and use the labels in order to interpret them.